Okay, in this lesson we're going to be simplifying radical expressions. We're going to start by watching a short video on how to do this, and then we'll try a few on our own.
Hello mathematicians. After today's lesson you will be able to simplify expressions involving square roots. You remember that the square root of a number is the side length of a square with an area equal to that number. So the square root of 16 is 4 because a square with an area of 16 would have a side length of 4 units. Since all sides of a square are the same length, finding the square root of a number a means finding some number that when multiplied by itself gives you a. So for instance, the square root of 25 is equal to 5 because 5 times itself equals 25. Also remember that while all numbers greater than 0 have a square root, only numbers called perfect squares have integer square roots. Trying to take the square root of a number that's not a perfect square will yield an irrational number. 18 is not a perfect square because 4 times itself is 16 and 5 times itself is 25. So the square root of 18 is somewhere in between 4 and 5, but it's an irrational number. However, sometimes it is possible and very useful to simplify square roots into smaller terms. We will simplify radical 18 in just a minute, but first I want you to think about something. Radical 4 is 2, and radical 9 is 3. When I multiply radical 4 times radical 9, I get radical 36, which I know is equal to 6. Now I could start the other way and start with radical 36, then break it up into two factors, radical 4 and radical 9, which would give me 2, because that's the square root of 4, and 3, because that's the square root of 9. And 2 times 3 is equal to 6, exactly what I expected when I would take the square root of 36 in the first place. This process of splitting a square root into factors could help you simplify numbers you may not know are perfect squares, such as the square root of 400. Well, you know that both 4 and 100 are perfect squares, and that 4 and 100 are a factor pair that multiply to become 400. So you can split radical 400 into radical 4 times radical 100. You know radical 4 is equal to 2, and you know radical 100 is equal to 10, so you get 20. So 400 is a perfect square, and its square root is 20. This same idea will help us simplify radical 18. Since 18 is not a perfect square, we will not be able to eliminate the radical completely, but we can make it simpler. Can you think of any factors of 18 that are perfect squares? 9, right. So I could split this into radical 9. 9 times what is 18? 2. 9 times 2 is 18, so we have to keep the radical 2 here as well. So this is an equivalent statement. Radical 18 does equal radical 9 times radical 2. But since radical 9 is equal to 3, I can replace the radical 9 with a 3. 2 is not a perfect square, so there's nothing I can do with the radical 2. I have to leave it as radical 2. So I can simplify radical 18 into 3 radical 2. This is still an irrational number, but a simpler form of this irrational number. It is simpler because it will allow us to complete operations with this irrational number a little bit later in algebra and algebra 2. Let's try another. Can you think of any perfect square factors of radical 24? How about 4? 4 is a factor of 24, and 4 is a perfect square. What is 4's factor partner when multiplying to be 24? It's 6. So I can rewrite radical 24 as radical 4 times radical 6. Radical 4 is equal to 2. Radical 6 is just an irrational number that I'm going to leave as radical 6. So I simplify radical 24 into 2 radical 6. One last one. Radical 30. From our experience with perfect squares, we can see this is not a perfect square. Does it have any perfect square factors? Well, it definitely has factors, such as 3 and 10. Radical 3 times radical 10 would equal radical 30, but neither of those is a perfect square, so neither of those will be able to be simplified. So that's not a good way to write it. What about radical 5 times radical 6? Again, that's a true statement, but neither of those is a perfect square, so neither of those can be simplified. So that's not a good way to write it. It turns out that radical 30 is as simple as it gets. It is an irrational number that cannot be simplified any further. So now you can simplify expressions involving square roots.
Okay, so let's continue. On this slide, you can see that we've kind of explained some of the symbols that we're using here. If b squared equals a, then b is a square root of a. Remember, the radical symbol is meaning the positive square root or the principal square root. If we want the negative root, it would be, we put the negative on the outside. So the negative square root of 9 means that we're talking about negative 3. And again, right here we have the notation. And sometimes when you're asked for the roots, as in plural, you would want to give both the positive and the negative to show that you understand. Positive 3 times positive 3 is equal to 9, and negative 3 times negative 3 is also equal to 9. So simplifying these radical expressions, you have this product property for radicals, meaning that if you have a number underneath, in this case they're showing it a times b to show you that they're actually distinct, but it's just two factors. It could be a whole number underneath the radical symbol that can be broken up into two of its factors. So the square root of ab is equal to the square root of a times the square root of b. This was in the video, so the square root of 36 is equal to the square root of 4 times the square root of 9. You can evaluate each individually, and then when you multiply, you can see that they're equal to 6. Same goes for 100. Another example. So radical has been simplified when its radicand contains no perfect square factors. So the radicand is the number that's underneath the radical symbol. So you look for perfect square factors, and if you need to use a factor tree, you can, but try dividing by some perfect squares like 4, 9, 25, 49, and so on until you can test the number to see if it has any perfect square factors. Again, you can use the factor tree, and we could definitely use a prime factorization way of doing this, but hopefully you won't have to if we can find these perfect square factors. So in this case, it would be the square root of 25 times the square root of 2. In simplified notation, you have 5 square root of 2. If they are variables, this is interesting to note if you can see the relationship between the square root of x to the 14th power. Now, if we were to write that out in expanded notation, you have 14 factors of x underneath the radical symbol, and for every 2 x's, right, for every x squared, 1 x would come out. So for even exponents under the radical symbol, you can divide the exponent by 2 and find out what it would be in simplified form. So if it's odd, we would have to put it into a different form. So here's your steps. Try to divide the radicand into perfect square for numbers, right? So look for perfect square factors. If there is an exponent, make it even by using the rules of exponents. Separate the factors to its own square root and then simplify. So simplifying the square root of 45. Think of 2 factors, and if one of them is a perfect square, use that, or they could both be perfect squares. So square root of 9 times square root of 5. 3 square root of 5 in simplified form. 49x. Again, in this case, we have 49 could be, well, already a perfect square, and it's times the square root of x, which is, in this case, an exponent of 1, not an even number. So it has to stay under the radical symbol. So 7 square root of x would be the simplified form. 45x to the 6th power. Note the exponent is positive. So we have the square root of 9, x to the 6th, because that is an even exponent. We know that we'll get x cubed out of the radical, times the square root of 5, 3x cubed square root of 5. 50 y to the 7th. So in this case, we have 25 times 2 that makes up the 50, and here's where we're talking about if there's an odd number for the exponent, you could definitely break that up into y to the 6th times y to the 1st power. So now we have the even exponent we were looking for, and then the leftovers. So the one on the left becomes 5y cubed, and underneath the radical is 2y. So it's irrational. The next thing I want to talk about has to do with the quotient property of simplifying roots. So for this quotient property, we saw a little bit of it in our previous lesson. If you have the square root of a over b, that's equal to the square root of a over the square root of b. Now you do not ever want to leave a radical in the denominator when you are simplifying. And I'll show you an example of something we can do right here. If, for example, I'm taking the square root of 4 over 3. And we can already tell the square root of 4 is going to be a perfect square, but the square root of 3 is irrational. Since we do not want to leave that square root of 3 in the denominator, I could multiply this whole expression by a factor of 1, and the factor of 1 I would choose would be square root of 3 over square root of 3. Anything over itself is equal to 1. Okay? So, if we evaluate the square root of 4, we would get 2. That would be times the square root of 3, because multiplying fractions, you multiply across. And the square root of 3 times the square root of 3 would be the same as taking the square root of 9. Therefore, the denominator would then become 3. We have kind of rationalized the denominator that way. Because it was irrational, we didn't want to leave it that way. Most of what you're going to see as you're just starting out will be similar to what we did yesterday, where everything is pretty much a perfect square, or you can put it in the right form so that it would be a perfect square. So let's try another example. Let's try to simplify this expression. Okay? Again, remember we said this would be the same as square root of 49 over square root of 121 x squared. It's 121 times square root of x squared, and if it's an even exponent you can divide by 2. Therefore, square root of 49 is 7, square root of 121 is 11, square root of x squared is x. 7 over 11x. Okay, and finally, one last slide to leave you with all of the new vocabulary terms and terminology that we've been talking about for the last few days. Square root, principal square root, negative square root, radical, radicand, perfect square, irrational number, rational numbers, any radical expression. Okay? And you may pause and refer back to this as often as you'd like.